Hello, we're just gonna jump right back. Okay. First half of this has the first half of the explanation. Watch that first. Here we go. Okay, so we're writing electron configurations. We just talked about how these are going to kind of look like Bohr and Lewis, where the extended version has all of the information and the core notation is based on the core. Great. Okay. I kind of want to tell you about how I teach this in person because it's completely different from how I'm doing it virtually, because I don't have a printer, so I can't hand you the data tables that we use. So we're just going to do this with the page you just built. And the big idea here is we're going to write the address. Okay, so electron configurations, what they do is they write the address of every electron in an atom. Okay. And the reason we built this whole monstrosity is to help us out. Okay, so yesterday's homework, you were looking at the size and shape of the outermost electron in each of these elements. Got the size, got the shape, cool. We then figured out that, as we've been saying for a long time, the D's and F's are weird, they're smaller than you think they should be. Cool, we got that. Where we're going next is we're going to say we can take any element and write the address of every electron inside of it. Okay, let's start with hydrogen, because that's a nice place to start. Hydrogen's up here. Hydrogen has only one electron because it's got only one proton, only one electron. Great. Only one thing we're keeping track of. Okay. And I'm just gonna dive in and give you some examples because I don't think that there's a lot more to say. I think we've said all the things we need to. We're just gonna do some examples. So example, hydrogen has only one electron. Hydrogen's one and only electron is in hydrogen's outermost electron is one and only outermost, is located in the 1s orbital, and there's only one. So to write the electron configuration of hydrogen, we're going to say its one and only electron is in the 1s orbital, and in that 1s orbital there is only one electron. So we've got the size, the shape, and the number of electrons in that orbital. Let's label this, even though you're like, seriously, we've been over this so much. So the number is size. You know that that's a number. Okay, the number is size. The letter is shape. And the little number up there that kind of looks like an exponent, it's not. It looks like an exponent, but it's not an exponent. This tells you the number of electrons in this orbital. Okay, so this is saying that in hydrogen's 1s, there's one electron. Let's do helium also. So helium is element number 2. Helium has 2 electrons. Helium is still located in the 1s orbital. So looking at helium, we write helium over with the noble gases, but it is the one element that's kind of like missing from the s block. Here's the s block. It's got lots of nice elements. Every s orbital only has one suborbital. Every suborbital can only hold 2 electrons. So every s orbital can only hold 2 electrons. That's why there's 2 columns here. 1s can hold 2 electrons. They are hydrogen and helium. even though helium's printed over there, it's still in the 1s. The 2s can hold 2 electrons. They are lithium and beryllium. The 3s can hold 2 electrons. They're sodium and magnesium. The 4s can hold 2 electrons. They're potassium and calcium, and so forth. So if we're writing helium, helium is in the 1s shell. Its outermost electron is in the 1s orbital. We're going to say helium's electrons are in the 1s, and helium has 2 electrons in the 1s orbital. Okay, let's just keep going. Lithium is element number 3. There are 3 electrons in lithium. Lithium's outermost electron is in the 2s, but just like a Bohr structure, we're going to write out everything including its core. So for lithium, lithium has this 1s core, and it's full. So lithium has 3 electrons. 2 of them are in the 1s core, and 1 is in the 2s. So lithium's outermost electron is in this 2s orbital. And just like a Bohr, count how many electrons are in that 2s orbital. Lithium has only 1 electron in its 2s orbital. Okay, I'm going to turn on my light. I'll be right back. You can fast forward to when this moves again. I'm recording this in the night. I got a little behind sending emails. Okay, I'm back. Okay, so lithium has 3 electrons. It's got that full core. Its 1s is filled with 2 electrons. Lithium's outermost electron is in the 2s orbital, and in its 2s orbital there is only 1 electron. Okay, we're just going to keep going because you're going to get the flow of it, but without the tools that I can hand you at school, it's going to take a little bit more, but that's okay. You're going to start to see a pattern and it'll be fine. So beryllium has 4 electrons. Its outermost electron is in the 2s orbital, and in the 2s orbital, beryllium, just like a Bohr, count the electrons, has 1, 2 electrons in its 2s. Beryllium also has full everything above it, just like a Bohr, everything above it is full. So beryllium's got a core of the 1s orbital that's full with 2 electrons. So beryllium, that inner core, the 1s, has 2 electrons, just like inside your Bohr structure. You've got that inside circle, the size 1 circle, with 2 electrons on it. Same thing here. That's like the inner core for the beryllium also. Beryllium outside electron is in the 2s, and inside the 2s you have 1, 2 electrons. So we're going to say 2s2. And, alright. So it's got a 1s, a size 1, shape S, core with 2 electrons in it. It's got a size 2s with 2 electrons in it. Let's just keep going on to boron. Boron is on the other side of the transition metals. So boron has the same starting reality as beryllium right next to it. Boron's over here. So boron, just like your Bohr structure, has its top row is its 1s, and it's full. It's got those 2 electrons. Boron's outermost electron is in the 2p. Okay, great. It's got 5 protons, 5 electrons. Its outermost electron's in the 2p. Boron over here has a full 2s. You can kind of just walk across your table and like write what you see, more or less. So the 1s is the first thing you run into. We're counting to 5, so the 1s is full with 2. The 2s is also full with 2 electrons. And boron is over here in the 2p. boron has 1 electron in its 2p orbital. So it's got a full 1s, a full 1s2, 2s2, and in boron's 2p, there's 1 electron in boron's 2p. You might be starting to see the hang of this. Let's try carbon. Carbon has 6 protons, 6 electrons. Start from the top. We're going to write out that core every time until I teach you core notation. So start from the top. Start from the 1s. Carbon's got 6 electrons. We're building up. Okay, so carbon's 1s is full. We've got 2 electrons in our 1s. Just like a typewriter, boop over to the next line. Here you've got your 2s. Carbon's 2s is full, 2 electrons, lithium, beryllium. Carbon is bigger than that. It's got a full 2s with 2 electrons in it. And then carbon is over here. Carbon's outermost electron is in the 2p. And in carbon's 2p orbital, it's got, count from the left, 2 electrons. So here's carbon's 2p, and in carbon's 2p, there are 2 electrons. Okay, you're starting to see a pattern. Nitrogen. Nitrogen's has 7 protons, 7 electrons. Its core is full. Its 1s is full with 2 electrons. Nitrogen has 7. Okay, so its 2s is full also with 2 electrons. Nitrogen's 2p has, start from the left, here's the 2p. We're going to count across. For nitrogen, 1, 2, 3. So nitrogen has 3 electrons in its 2p orbital. Okay. I'm going to leave some of these undone on screen so that I can ask you them as homework questions. But let's try, we're just going to do some examples with like outermost electrons in a bunch of different shells. Okay, so we've done a lot of examples from the 2p. Once we fill our 2p up with 6 electrons at neon, let's do neon. So I'm going to show you a full 2p. Nitrogen is N, neon is Ne. Okay, so neon has 10 protons, 10 electrons. And start from the top. So neon's 1s is full. It's got 2 electrons, hydrogen, helium. Boop over to the next line. Neon's 2s is full. We're counting up to 10 total, so 2, 4. We haven't gotten anywhere close to 10. Switch over to your 2p. Here's neon. Here's your 2p orbital. You've got 1, 2, 3, 4, 5, 6 electrons in neons. That might have gone too fast. Okay, so this is the 2p. Here's neon. In neon's 2p, count across, that's where I got that 6. There's 6 electrons in neon's 2p. And at that point, the 2p is full, and we actually can't put any more electrons in it. Referencing over here, we wrote this, I don't know how many days ago by now. Each suborbital can hold 2 electrons. So you've got 3 suborbitals in your p. Each of them can hold 2 electrons, so you're looking at 2 times 3 is 6 electrons. So your p orbital is full once you hit 6 electrons. Yeah. Alright, so our 2p is full. Let's move over to the next line. 3s. Let's do one of the elements whose outermost electron is in the 3s. We'll do magnesium, because why not? Okay, so magnesium is here, 12 electrons. Okay, start from the top. Magnesium's 1s is full, hydrogen, helium. We're bigger than that. We've got 2 electrons in our 1s. Next line, 2s, also full, with 2 electrons. Magnesium's down here on the 3rd row, so magnesium's 2p is also full. And if you're not sure, you can count. But magnesium's on the 3rd row. Okay, so its 2p is going to have all 6 electrons filled in. Because magnesium is bigger than neon, so it's got a full 2p core inside. Okay, magnesium's bigger, so we're still adding stuff here. Magnesium's outermost electron is in the 3s orbital, so we need a 3s. And in that 3s, we have 1, 2, count from the left, just like a Bohr, 1, 2 electrons in that 3s. And that is magnesium. So, among other things, what you're seeing here is that you could get just this information. I could give you just the electron configuration, and you could tell me what the atom is. Just like I could give you a Bohr, and you could say what atom the Bohr structure is of, because you have all the information you need. Even if we take out which element it is, what you can see is that this element has a full 1s with 2 electrons, a full 2s with 2 electrons, a full 2p with 6 electrons, and a full 3s with 2 electrons. So on your table, you would count it, you would say, here's my 1s, 1, 2 electrons, my 1s is full. Here's my 2s. Okay, here's my 2s on my periodic table, 1, 2, 2s is full. Here's my 2p. Here's my 2p, 1, 2, 3, 4, 5, 6, 2p is full. 3s with 2 electrons, okay, here's my 3s, and with 2 electrons, that must be magnesium. So you can kind of think this through forwards or backwards, and I can either give you the symbol of the element, and you can write the electron configuration, or I can give you the electron configuration, and you can find the element. I feel like that just was a lot of words and things. Let's do some more examples, because I think you're like starting to get the flow of this, but there are a lot of elements on the table, so let's just do some more. Let's do phosphorus. I'm looking for my pen so I can make this really bold. Okay, so here's phosphorus. Phosphorus is right under nitrogen. It is element 15. I'm just going to fill in some of this stuff kind of as I go, because I don't want to make you sit there and like write all of the elements into your table. Okay, so there's phosphorus. It's element 15. Already you're thinking to yourself, okay, 15 is bigger than 12, so I'm going to be putting more electrons than magnesium. And you also may be thinking phosphorus's outermost electron is in the 3p. You might also be thinking that in the 3p for phosphorus, you've got 1, 2, 3 electrons. So its outermost shell is going to be this, include this 3p with 1, 2, 3 electrons. Okay, but first things first, the extended form, this is like the Bohr structure, these get long, and you will be writing long extended electron configurations because just to make sure that you can do the whole thing, whereas like drawing a huge Bohr is just a little absurd. Okay, so we're doing phosphorus. Phosphorus has 15 protons, 15 electrons. Start from the top. Phosphorus's 1s is full, hydrogen and helium, just like the inside core of your Bohr, except now instead of drawing circles, you're just writing 1s2. Hydrogen has 15 electrons. Okay, so lithium, beryllium, hydrogen's 2s is full with 2 electrons. Okay, here's the 2p. Phosphorus is down here in the 3p. Phosphorus's 2p is full with all 6 electrons. So 2p is filled with all 6 electrons. There's 2p. Okay. Phosphorus is in the 3p, so we're back over here at the beginning of the third row. Here's your 3s. Phosphorus is 15, bigger than 12, so our 3s is full with 2 electrons. Phosphorus is in the 3p, so over here in the 3p, we know we've got something in the 3p. And phosphorus is here. Start from the left and count. 1, 2, 3. There are 3 electrons in phosphorus's 3p. And I'm going to say this. We go deeper when we're in person. The 3 electrons in phosphorus's 3p are evenly distributed between these 3 orbitals. So phosphorus has 1 electron in its p X, 1 electron in its py, 1 electron in its pz. That's just, the electrons are all negative, they repel each other, they would like to be as far apart as possible. When when you're distributing electrons between these orbitals, you put one in each orbital and then go back and put a second in each orbital, because each suborbital can't hold 2 electrons, but if they can, the electrons will spread out between these 3 suborbitals. Yeah, let's just leave it like that. Oh, actually, and the same thing, we're going to take it one step further. The same thing happens in the D and the F orbitals as well, or suborbitals. So if you have 5 electrons in a D orbital, they're going to spread out between these 5 suborbitals equally. So you're going to get 1 in each of the 5 suborbitals, and then that 6th one will go back and double up in the first orbital. The 7th will double up in the 2nd, the 8th will double up in the 3rd, 9th double up in the 4th, etc., etc. Same thing in the Fs. If you have 1 electron in the Fs, it'll go into, you can have 7 unpaired, is how we say it. 7, by themselves. 7 orbitals with a single electron in each orbital in the F. Because if you only have 6, they'll spread out as much as they can. If you have 7, they'll spread out as much as they can. It's only when you get to 8 that they start to double up and have both of these 2 electrons in each suborbital. You're thinking, why do I care? What you don't know is that you care because these unpaired electrons are what we call magnets. Anything that is a magnet is caused by unpaired electrons. We say they're spinning in the same direction. So unpaired electrons spin in the same direction. When you have only 1 in each of your suborbitals, it kind of creates magnetic pull. So if you look at your table and you're looking for the strong magnets that you know of, they're probably somewhere in the middle of this transition metal block, because here is where you have your d orbitals. Everything in this column has 1 unpaired, so these are kind of magnets. These are a little bit more magnets. These are more magnets. These are pretty magnetic. Over here, you've got some strong magnets here. Here's where you start to kind of double up again. Now you've got some doubled up. As it doubles up, the magnetic pull decreases because now you have a balance instead of unpaired spin electrons. So your strongest magnets are in here. Some of the magnets on your fridge are probably in here. If you have a magnet that falls off your fridge all the time, it's probably over here in the somewhat less fewer unpaired electrons kind of regions. Either because there's only a couple electrons in the D block at all, or they're mostly paired up and they're mostly paired up over here. You're like, hey, you're talking about the D block. I thought you just said that the F block could have 7 unpaired electrons. Okay, let's look at your F block. Okay, here in your F block, you've got 1 unpaired electron. Now you've got 2, 3, 4, 5, 6, 7. So in here, in your D block, in your F block, you start to get lots of unpaired electrons spinning the same direction, is what we say, and that unpaired spin causes crazy magnetic pull, and so, which is why we haven't gotten to properties yet, but so I don't want to steal your thunder. If you're in the inner transition metal group, you may have talked about how the new research on how to make things, your technology faster, better, stronger, is all in these F block stuff, because you can make your electrons kind of jump around a lot and it's those little tiny jumps and crazy strong magnetic spin that makes these really, really strong elements. Good. That was a tangent. Okay. But, we got there because we were talking about how phosphorus has 3 electrons in its 3p. So even something like phosphorus in the p orbital region, the p block, phosphorus and nitrogen and everything in this column has 3 unpaired electrons in their p orbitals. And these are actually all pretty strong magnets also. Who cares? I mean, I get it if you're like, I don't really care. This helps you take photos of things. You can bump it with a really strong magnet and then take a picture of it and see where all your atoms are. I mean, also they're just magnets, which is kind of interesting. They interact with electricity in different ways than like non-magnetic elements. Okay, anyways, so things like so phosphorus is like kind of a magnet. It's got 3 unpaired electrons. That's not going to be as strong as like iron, which has more like 5 unpaired electrons or something. 1, 2, 3, 4, 5, 6. Okay, so iron has 4 unpaired electrons and 1 paired up. Anyways, I'm getting ahead of myself. Electrons spread out as much as they can because they're all negative. Okay, speaking of transit, let's just do iron because we're talking about transition metals. Iron is here. Okay, iron was the kind of element where yesterday night you would have predicted that iron was size 4. However, you would have said it's in the D block, and I think it's actually smaller than I think it is. Okay, so here's the periodic table that you just drew earlier today. Iron is number 26. I'm going to take my big bold marker and mark number 26 as iron. There we go. Let's do an electron configuration for iron. Okay. 26 electrons. We're going to write out the whole core. Here we go. Let's do 2 more long ones and then show you the short ones. Okay. So iron has 26. I'm going to do some of this a little bit faster and start saying the words for it. So it's got a full 1s. We say 1s2. That's not squared. That's 2, by the way. So we say 1s2 just means a full 1s with 2 electrons. 1s2, its 2s is also full with 2 electrons. So 1s2, 2s2. Iron has full 2p with 6 electrons. 1s2, 2s2, 2p6. There's this like rhythm to it. Okay, come over here to the 3 s's. Iron is still all the way over here, right? So we've got a full 3s that we're looking at. So 3s is full with 2 electrons also. Over to your 3p's. Iron is number 26. Your biggest 3p is 18. Iron's bigger than the 3p's, so it's whole 3p is full, 3p6. Take yourself to your 4 s's. The biggest 4 s is calcium with 20 electrons. Iron has 26. We're even bigger than the 4 s's, so your 4s is full. Your 4s is full with 2 electrons. And your iron, we're getting close to your iron finally, element 26, 26 electrons. Iron is in the orbital, the 3d orbital. So it's got the size of the 3s orbital, but the shape of the d, because the energy of that weird shape is such that it's a smaller size because the energy of the orbital itself is so intense. Okay, so it's size 3 and shape d. Okay. And we want to know in the 3D how many electrons there are when we get to iron. So just like your board, start from the left. You're only looking at the 3D right now, okay? So you already put these 2 and the 4s over here. Now you're just looking at the 3D, and you've got 1, 2, 3, 4, 5, 6 electrons in your 3D orbital when we run into iron. So just to show that again, we've already accounted for these 2 and the 4s. We're only looking at the 3D now, so start from where this D block starts over here, and so where the transition metal starts, and how many electrons in the 3D orbital. We've got 1, 2, 3, 4, 5, 6. Okay, so we write that up here. We say 3d6. All right, and this, I could hand you this. You could use your table and say, well, my 1s2, 1s is full, 2s2, 2s is full, 2p6, my 2p is full, 3s2, 3s is full. We did 3s2 over here. That's magnesium when 3s is full. 2p6, or I mean 3p6, 4s2, 3d6, you could use this to figure out that this element, you could use this electron configuration to figure out that this element is, and I just revealed that as if that made sense. We would do it by counting your 3d orbital until we have 6 electrons. So start from the side, 1, 2, 3, 4, 5, 6. At the point you hit, at the point you hit 6 electrons in your 3d, you're sitting on iron. And just from, if you were given this electron configuration, you could figure out that that atom is iron. I'm going to do an even more wild electron configuration just to show that you can. And you might be writing a wild one for real on your own in the wild at some point. I was going to do, let's do uranium and tin, because those are both pretty nuts. And things that you've like heard of before, so that's nice. Actually, let's just go nuts. We're going to do, okay, fine. We'll do both. Okay, so tin is element 50. There's 50 valence electrons in tin. Tin is over here. That's not on the screen. Okay, tin is over here. Okay, so this is going to be a longer sentence because it's a bigger atom. But even here, already, we can see tin is in the p block. This whole thing is the p block. Tin is definitely in the p block. We know that S's and P's are the size that we think they should be. So we can take our tin atom and kind of back up, boop doop 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 doop, and we can say that the outermost valence electron of tin is size 5. And now we know that tin's outermost electron is in the p block. It's got the shape of a p, and it's size 5. That's kind of cool. We don't even have to. And here's our goal. Our goal is to get you reading this like a book, so that I can choose any element on the table. You don't have to know a thing about it, and you can actually tell me a fair bit based only on where it's located. So you know something about tin. You've probably seen a tin can before. And now you also know that you can figure out that the tin atom is size, its outermost electron is size 5, and it's in the p block, so it's got a shape of a p orbital, those petals. And you could even, just from its location, tell me that you know the p block starts here. I'm going to cover up the d block entirely. We know the p block starts here. Here's our 5p. Already, here's tin. You know there are 2 electrons in the 5p. I feel like that might have just gone a little too fast. So let's do the whole thing. And it's not going to be so bad, even though we're doing something with 50 electrons. You'd have to draw 5 circles if you're doing this as a Bohr. Tin is Sn, because that makes sense. And let's just do it. Okay, so tin is 50 electrons. We know, we're totally sure it's 1s is full. We say 1s2, there's 2, just like the innermost Bohr would have 2 electrons on the inside circle. I'm actually just going to do this one partially to get you the flavor of the language, and rewind and ask questions and all that. Okay, so I'm going to build this to 50 electrons. Here we go. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 4s2. When I run out of a line, I just go over to the next line. So I ran out of the 3p's, so now I'm here at the 4s's. 4s2. (3d). Okay, how many are in a full 3D? Let's do this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And that makes sense because there's 5 suborbitals and they each hold 2 electrons. So we would guess there'd be 10 electrons in a full d orbital. Okay, so it's size 3, shape D, and it's got 10 electrons because it's full. After our 3 Ds, we hit the 4 Ps, and we're going to tin, which is element 50, so our 4 Ps are full. That's, our 4 Ps are full. A full P has 6 electrons, you can count. That takes you to the end of the 4 Ps. 5s, it's full with 2. We like the S's, they're simple. 5s2. 4d, and we're making our way over to the 5p. Okay, so we've got a full 4d. How many electrons in a full 4d? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That is exactly what we thought it would be. 4d full with 10. Now you're over to your 5p. Here's tin. Your 5p starts where the transition metals end. In your 5p, once you get to tin, counting 1, 2. I'll make this nice and bold too. So here's where we're going to, is tin right there. And in our 5p orbital, we've got 1, 2 electrons. Okay, so this is an example of a sentence that gets a little bit longer. I said uranium. I've got to do it now. Uranium. I'm just gonna, yeah. Okay, here we go. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, here's my transition metals, 3d10, 4p6, p's are the size you think they should be. Now we're going to start the beginning of the 5th line, 5th row, 5s2, thank goodness for the s's, right? Uranium is 92, I think, or something like that. Oh, good. Oh, perfect. I gave myself something in the F block. Why did I do this? Okay, it's in the F block. It's on the 2nd row of the F block. It's on row 7, but we know that the F shape is so weird that this is the 5F in the middle of the 7th row. Okay, so I only checked that because I was like, is it in the 5th row? Am I getting close? No, we're not there yet. Okay, we're still in the 5th row. 5th row, here's our 5s. 2 electrons in the 5s. Now we're into the Ds. The Ds are one size smaller than you think. So they're size 4D, but this one is full also, and a full D has 10 electrons. Now we're over to the 5Ps. That's full with 6. Okay, here's the 6th row. 6s2. Rows always start with the s orbital, which is like awesome because you can kind of keep track there. Okay, so there's our 6s with 2 electrons. Now we're off to the f's. Good, good, good. Okay, so this is on the 6th row, but the f's are so weird. They're 2 sizes smaller than you think they should be. That is the 4f. Great. Okay. How many electrons are there in the f orbital? Well, depending on which table you printed, this could get weird, but what you do know is that there's 7 suborbitals, each of which can hold 2 electrons. 7 times 2 is 14. Count across. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I should actually count this. If you've got 15 instead of 14, it's because they printed a blank in the middle of the actual table. We did not do that on our table here. we put 14 elements in your F blocks here. There are 14 electrons in a full F orbital. Okay, and our 4F in this case is full, so it's got 14 electrons. I'm going to zoom in a little bit on this end stuff because this is where it gets messy, and you're like, oh good, this is where it gets messy. Okay, so 6s2, 4f. Now pull yourself back up to the main block. Now you're into the D's. 6s, 4f. Back to your D block, your transition metals. These are weird. They're only a little weird. They're one size smaller than you think. This is your 5D. 5D. A full D can hold 10 electrons. Once we get through your 5D, we get to your P block. Your P block is the size it should be. This is your 6P. 6P, and it's full with all 6. We're getting close, which is nice because I ran out of space. So I'm going to start again on this line with my 7s. 7s is just this bit right there. Those are full. We're like actually getting close because uranium's here, and we just got to 88 and we're going to 92. Okay, so this is your 7s2. Here's your F. Your F is 2 sizes down from what you think. That's a 5F. 5F. In your 5F, count across to uranium. 1, 2, 3, 4. So in a uranium atom, its 5F orbital has 4 electrons. Oh, look at that. It's all on the screen. Okay. If your head is spinning, sorry. I haven't even shown you chord notation. Okay, let's end it here with this. This is the more important part. Core takes the core and abbreviates it. So a core is anything that is full through its p orbital. So actually neon is a core because this is a full p. Neon you could write as like that. Magnesium, here's your full P. That full P is neon, so you would write magnesium as neon, a neon core plus 3s2. Phosphorus you could write as a neon core plus 3s2, 3p3. I feel like this is enough information, and we're just, for tonight, we'll write some full electron configurations like these. These are all examples you can use, by the way. Secretly, I did number 92 uranium because anything I give you that's less intense than uranium, you've got a template for right there. So this will look a lot like yesterday, except you're going to be writing some electron configurations and use these as examples. I'll post a couple questions for you, and good luck.